Right now, the farthest object humanity has ever launched is drifting through the freezing dark of interstellar space at 38,000 miles per hour. At that staggering velocity, reaching the nearest neighboring star would still require 73,000 years of unbroken flight. We look up at the night sky and see thousands of exoplanets confirmed by modern telescopes. The destinations are absolutely real. But what if the void between solar systems is not merely empty space, but a deeply engineered defense mechanism? The cosmos did not build a single wall to keep us bound to our sun. It constructed a lethal, interlocking chain of them. Distance, energy, radiation, and the fundamental laws of physics are linked together, ensuring that whenever a traveler attempts to solve one catastrophic problem, the solution itself creates an entirely new nightmare. We are about to examine the absolute limits of human ambition as it collides with the cold geometry of reality. If you find a strange comfort in the profound mysteries of the dark, subscribe to Bedtime Universe and settle in. The stars have always called out to humanity, echoing across the vacuum. It is time to understand why the universe might never allow us to answer. Human intuition fails profoundly when it attempts to process the architecture of the cosmos. The human brain evolved to comprehend distances that a physical body can walk, territories that a hunter can cross, and horizons that a naked eye can scan. Nothing in the long evolutionary history of our species prepared the mind to hold interstellar distances as real, tangible quantities, rather than abstract mathematical symbols written on a page. Every civilization that ever looked at the night sky asked the exact same question about what exists out there in the dark. The Polynesians navigated thousands of miles of open ocean using nothing but the positions of the stars and the patterns of the waves. The ancient Greeks imagined massive celestial spheres carrying points of fire across a grand dome of darkness. Chinese astronomers recorded bright supernova events that were visible to the naked eye, wondering deeply about the unseen forces that could make a star explode. Aboriginal Australians read the dark spaces between the stars, building complex stories from the shape of the absence itself. Every culture on every continent across every century stared upward and felt the exact same pull. The stars were calling, and humanity possessed a deep desire to answer. That desire never faded away. Instead, it grew and sharpened over time. Modern science inherited this ancient longing and added something highly dangerous to it, which was precision. Researchers learned to measure the exact distances to nearby stars and calculated the immense energy required to reach them. They designed theoretical spacecraft on paper, simulated complex trajectories on computers, and identified specific worlds and specific atmospheres that might harbor biology. Astronomers have already confirmed more than 5,000 exoplanets orbiting nearby stars, some of which sit directly in habitable zones where liquid water could potentially exist on rocky surfaces. In the year 2026, researchers identified 45 rocky worlds as top habitable zone targets, including the 7-planet TRAPPIST-1 system roughly 40 light-years away, and Proxima Centauri at just 4.24 light-years away. The James Webb Space Telescope is actively analyzing the atmospheres of these worlds right now, searching for chemical signatures that might indicate biology. The targets are absolutely real, and the destinations definitively exist. The numbers that came back from all of this modern precision were not merely large. They were a completely different category of large. A kind of large that fundamentally breaks the relationship between human ambition and physical possibility. The question has never been whether there is somewhere worth going, but rather whether the physical universe will ever allow a crossing. The answer begins with distance, but not distance as human beings normally experience it. It is not the kind of distance that patience and a full tank of fuel can eventually overcome, but a distance so extreme that it transforms every single variable in the problem, making the journey itself physically hostile to the traveler. This is where the first invisible wall rises. Right now, the farthest human-made object in existence is a spacecraft roughly the size of a small car, drifting silently through the darkness beyond our solar system. Voyager 1 launched from the Kennedy Space Center on September 5, 1977, with an original mission to study Jupiter and Saturn up close. It completed that mission decades ago, and since its flyby of Saturn in November of 1980, Voyager 1 has been traveling on the exact same trajectory at the exact same speed, heading continuously outward into interstellar space. In August of 2012, it crossed the boundary of the heliosphere, which is the protective bubble of charged particles generated by our Sun, becoming the very first human-made object to enter interstellar space. It has been out there alone ever since that moment. On November 18, 2026, at roughly 2:16 in the morning Pacific Time, Voyager 1 will reach another staggering milestone. The National Aeronautics and Space Administration confirmed in its April 2026 status update that Voyager 1 will become the first human-made object to reach one full light day from Earth. One light day means that a radio signal traveling at the speed of light, which is the fastest anything can possibly move in this universe, will take 24 hours simply to reach the spacecraft. Mission controllers send a command in the morning. Wait all day, wait all night, and the response finally arrives the following morning. It takes a full day for light itself to bridge the enormous gap. Voyager 1 travels at approximately 17 kilometers per second, which is roughly 38,000 miles per hour, or about 61,000 kilometers per hour. At that extreme speed, an object could circle the Earth in roughly 40 minutes, reach the Moon in roughly 6 hours, or cross the distance from Earth to Mars at its closest approach in fewer than 60 days. Voyager 1 is incredibly fast by any standard human beings have ever applied to a moving object, and it has been flying continuously for nearly 50 years. In that entire time, it has covered roughly one light day. The nearest star to our solar system, Proxima Centauri, is not one light day away. It is 4.24 light years away. A single light year contains 365.25 light days, meaning Proxima Centauri sits approximately 1,550 light days from Earth. After half a century of uninterrupted flight, Voyager 1 has crossed less than 1/500th of the distance to the closest star. If Voyager 1 were aimed directly at Proxima Centauri, which it is not, it would arrive in approximately 73,000 years. 73,000 years ago, modern humans were sharing the planet with Neanderthals. The entire recorded history of agriculture, writing, cities, mathematics, empires, industry, and space exploration fits quite comfortably inside the last 10,000 years. Voyager would need 7 times that entire historical span just to reach one single star. As of mid-2026, Voyager 1 is over 166 astronomical units from Earth. An astronomical unit is the average distance from Earth to the Sun, roughly 93 million miles, meaning Voyager has traveled more than 15.8 billion miles. It sounds extraordinary, and it truly is extraordinary. Yet it is almost nothing compared to the true scale of the interstellar gulf. Proxima Centauri lies roughly 268,000 astronomical units away. After the longest continuous journey in human history, our fastest spacecraft has covered approximately 0.06% of that total distance. A detail that makes this scale even more disorienting is that Voyager 1 has not actually left home yet. It crossed the heliosphere in 2012, passing beyond the bubble of charged particles streaming outward from the Sun, and it now flies through interstellar plasma rather than solar wind. However, The Sun's gravitational territory extends far beyond the heliosphere. Our star holds a vast, diffuse spherical shell of icy bodies in its gravitational grip, known as the Oort cloud. This enormous reservoir of comets and frozen debris is believed to begin at roughly 2,000 astronomical units from the Sun and stretch outward to as far as 100,000 astronomical units, which is approximately 1.5 light-years. It marks the true gravitational boundary of our star's domain. Voyager 1, currently at 166 astronomical units, has not even reached the inner edge of this icy shell. It will not enter the Oort cloud proper for centuries, and it will not clear the outer boundary for roughly 30,000 years. By the time Voyager finally exits the Sun's gravitational sphere of influence completely, the civilization that built it will need to have survived longer than the entire span from the first cave paintings to the present day. After 30,000 years of flight, Voyager will still not even be halfway to Proxima Centauri. The heliosphere was never the actual border. It was merely a curtain inside a much larger room. Voyager 1 has pushed through the curtain, but the door is 30,000 years ahead, and the nearest neighbor is 40,000 years beyond that door. Our fastest, most distant traveler has not even finished the basic act of leaving home. To make this vastness tangible and bypass the evolutionary limits of the human mind, one must shrink the entire solar system down to a comprehensible scale. If the Sun becomes a basketball sitting on a sidewalk in New York City, Earth would be a small grain of sand orbiting roughly 26 meters away, or about 85 feet. Jupiter would be a marble about 135 meters from the basketball, roughly a block and a half down the street. Neptune, the outermost major planet, would be a small pea sitting roughly 800 meters away, about half a mile from the Sun. The entire known solar system from the Sun out past Neptune's orbit fits neatly within a modest walk through a single burrow. Voyager 1, after nearly 50 years of flight, would have traveled roughly 40 blocks beyond Neptune at this scale, about 2 miles past the edge of the solar system, meaning it would still be in Manhattan. At this exact same scale, the nearest star, Proxima Centauri, would be another basketball sitting on a sidewalk in Honolulu, Hawaii, over 4,000 miles away from New York. Between those two basketballs stretches nothing. There are no gas stations, no landmarks, no waypoints, and no emergency shelters. There is just 4,000 miles of bare table with a few grains of sand clustered near one basketball and absolutely nothing at all until you reach the other. This model is not an exaggeration. If anything, it significantly understates the terrifying emptiness. The interstellar medium, the material that fills the space between stars, averages roughly 1 hydrogen atom per cubic centimeter. The air humans breathe contains approximately 25 billion molecules per cubic centimeter. Interstellar space is not merely empty. It is a void so thorough that it challenges the very meaning of the word emptiness itself. Laboratories on Earth cannot produce a vacuum this clean, as the best vacuum chambers ever built still contain millions of molecules per cubic centimeter, which the space between stars puts to absolute shame. This extreme scale dictates why interplanetary travel and interstellar travel are not simply different points on the same spectrum. They are fundamentally different categories of problem, where the distinction is not one of degree, but one of kind. Humanity has achieved genuine triumphs of engineering and determination within the solar system. Rovers have landed on Mars and driven across its surface for years. A probe was dropped onto Titan, the moon of Saturn, photographing its methane lakes. Spacecraft have flown past every major planet, including Pluto at the edge of the solar system, and an observatory is parked 1.5 million kilometers from Earth at the second Lagrange point. Yet, all these triumphs share one critical feature. They were accomplished within a region where distances are measured merely in light minutes or light hours. A signal from Earth to Mars takes between 4 and 24 minutes, depending on orbital positions. That delay is entirely manageable. Mission controllers can send a command and receive confirmation within an hour. Software can be uploaded, errors can be corrected, and trajectories can be adjusted in real time. The spacecraft remains within the communicative reach of its builders, allowing problems to be diagnosed and solved from the ground. This ability to maintain a functioning relationship between the machine and the people who built it is what makes interplanetary exploration possible. The jump to interstellar distance breaks this relationship entirely. The distance to Proxima Centauri is roughly 700,000 times the distance from Earth to Mars at its closest approach. This is not a percentage increase, it is a multiplication by a factor approaching 1 million. The tools and strategies that conquered solar system distances absolutely do not transfer. When a Mars rover develops a software glitch, engineers at the Jet Propulsion Laboratory can diagnose the issue and upload a fix within a single day. If a spacecraft 4 light-years away develops that exact same glitch, the earliest Earth could learn about the problem is 4 years after it occurs. The earliest a fix could arrive is 8 years after the malfunction. By then, the mission may be completely over, the crew may be dead, and the systems may have cascaded into failure modes that no software upload can reverse. Communication delay is only one severe consequence of this distance. Resupply becomes physically impossible, as there is no cargo vessel fast enough to ever catch an interstellar spacecraft. Every gram of food, every liter of water, every replacement component, and every medication must be carried from the very moment of launch or manufactured aboard the ship. Rescue becomes a completely meaningless concept. If something goes catastrophically wrong 2 light-years from Earth, absolutely no one is coming. The crew is totally alone with whatever they brought and whatever they can build. To appreciate the vastness of the technological gap, consider the fastest spacecraft humanity has ever built. The Parker Solar Probe, launched by the National Aeronautics and Space Administration in 2018, holds the all-time speed record for a human-made object relative to the Sun. During its closest approaches to the solar surface, it reaches speeds exceeding 190 kilometers per second, roughly 430,000 miles per hour. That is fast enough to travel from New York to Los Angeles in about 20 seconds. Yet, even at the Parker Solar Probe's absolute peak velocity, a journey to Proxima Centauri would take approximately 6,700 years, which is longer than the entire span from the construction of the Great Pyramid to this exact moment. The probe only hits that speed during brief gravitational slingshots around the Sun and cannot sustain such velocity. Voyager 1's steady cruise of 17 kilometers per second is far more representative of what current propulsion can maintain over long durations. New Horizons, which flew past Pluto in 2015, cruises at roughly 14 kilometers per second. Pioneer 10 and Pioneer 11 drift outward at roughly 12 and 11 kilometers per second, respectively. None of these spacecraft were designed for interstellar missions. They were built for planetary encounters and simply kept going because nothing stood in their way. Chemical rockets, the foundational workhorses of the space age, produce exhaust velocities of 3 to 5 kilometers per second. The most advanced ion engines tested in space achieve 30 to 50 kilometers per second. Reaching even 1% of the speed of light, roughly 3,000 kilometers per second, would require a genuine revolution in propulsion technology that currently does not exist outside of theoretical papers. And even at 1% of the speed of light, Proxima Centauri is still over 420 years away. Interstellar distance generates entirely new categories of problems that have no equivalent at shorter ranges. Biology becomes a barrier because bodies do not live for centuries. Mechanics becomes a barrier because machines do not last for centuries. Sociology and psychology become barriers because civilizations do not hold together in permanent confinement. Distance forces a terrible choice upon the traveler, splitting the path into two corridors, and both corridors are heavily mined by the fundamental laws of physics. The architecture of the interstellar gulf forces every potential traveler into a brutal dilemma, presenting two distinct corridors of approach that both eventually collapse under the weight of physical law. The first corridor offers the illusion of patience, proposing that if the distance is too vast for speed, then time itself must become the vehicle. This is the concept of the generation ship, an idea that has captivated thinkers for nearly a century, from Konstantin Tsiolkovsky, who described it in 1928 as a kind of Noah's Ark equipped with engines, to extensive modern engineering studies like Project Hyperion. The logic appears deeply elegant at first glance. By building a vessel large enough to sustain a community and accepting that the journey will take centuries, a civilization seemingly bypasses the need to break the laws of physics with exotic relativistic propulsion. Generations would be born, live and die aboard the ship, passing the mission forward until distant descendants finally step onto the surface of another world. Yet, when this concept is measured against the actual mechanics of the universe, it does not sidestep the physical barriers at all. It merely trades the immediate hazards of speed for the slow, grinding erosion of time. Time, given enough of it, systematically dismantles everything human beings have ever constructed. Even the most powerful propulsion system ever seriously studied, the nuclear pulse engine proposed in Project Orion, maxes out at theoretical speeds of 3 to 5% of the speed of light, placing Proxima Centauri roughly 85 years away. More realistic nuclear thermal or electric systems, the kind currently in development for Mars missions, operate at fractions of a percent of light speed, meaning the nearest star remains thousands of years away. The generation ship must function perfectly, in total isolation, with absolutely no external help, for longer than most civilizations on Earth have ever lasted. The first force that begins to kill the crew operates entirely unseen. Beyond the protective cocoon of Earth's magnetic field and atmosphere, deep space is saturated with lethal radiation. While solar particle events produce intense bursts of protons that can be sheltered against, the true horror of long-duration travel lies in galactic cosmic rays. These are high-energy particles, predominantly protons but including heavy nuclei like iron, that originate from catastrophic cosmic events outside the solar system, such as supernova remnants and black hole environments. Traveling at nearly the speed of light, a single galactic cosmic ray iron nucleus carries more kinetic energy than a professionally pitched baseball, compressed entirely into a projectile smaller than an atom. On Earth, humans receive a background radiation dose of roughly 2 to 3 millisieverts per year, and astronauts on the International Space Station, partially protected by the magnetosphere, receive roughly 150 to 200 millisieverts per year. In the unshielded void of interstellar space, the dose from galactic cosmic rays alone climbs to 600 millisieverts per year or higher. Within 5 to 10 years of such exposure, every person aboard a generation ship would exceed the maximum lifetime radiation limits currently set for astronauts, leading to dramatically rising cancer rates and accelerated cardiovascular disease. More terrifyingly, research involving simulated galactic cosmic ray fields demonstrates persistent, irreversible damage to brain structure. Hippocampal neurogenesis, the fundamental biological process by which the brain forms new neurons essential for learning and memory, declines significantly after exposure to heavy iron radiation. This cognitive damage persists for the lifetime of the organism, but attempting to stop these microscopic projectiles introduces a cruel paradox of physics known as spallation. When a high-energy heavy nucleus strikes a conventional metal hull, it does not safely embed itself. it violently fragments, producing a secondary shower of neutrons, protons, and lighter nuclei that can be vastly more biologically destructive than the original particle. Add thicker aluminum or steel to the ship's armor actually increases the radiation dose inflicted on the crew. Effective shielding requires meters of hydrogen-rich materials, such as water or polyethylene, wrapping the entire habitable volume, which adds thousands or tens of thousands of tons of dead weight to the ship. Every kilogram of this shielding competes directly with the food, fuel, and equipment needed for survival, and even then, the dose is only reduced, never eliminated. Over centuries in the dark, this exposure accumulates, weaving genetic damage into the population's gene pool, guaranteeing that a ship launching with a healthy crew would eventually arrive carrying centuries of radiation-induced mutations. As the DNA degrades, the macroscopic structure of the human body simultaneously begins to dismantle itself. The human form was meticulously sculpted by 4 billion years of evolution under the relentless pull of one Earth gravity. Data from astronauts spending mere months in microgravity reveals a consistent, devastating pattern of physical unraveling. Bone density plummets at a rate of 1 to 2% per month in load-bearing areas like the hip and spine, while muscles rapidly atrophy despite rigorous daily exercise regimens lasting 2 hours or more. The cardiovascular system weakens, and the heart itself fundamentally changes shape, becoming more spherical as it no longer needs to fight gravity to pump blood upward. Fluid redistributes toward the head, dangerously increasing intracranial pressure, which deforms the eyeball and affects the optic nerve, a condition classified as spaceflight-associated neuroocular syndrome. While low Earth orbit astronauts eventually return to the surface to recover, a generation ship offers absolutely no return to gravity. Over multiple generations born and raised in this environment, the cumulative skeletal and muscular deterioration would inevitably produce a population completely incapable of standing up under the gravity of the alien world they traveled millennia to inhabit. The standard engineering countermeasure is artificial gravity through centrifugal rotation, spinning the habitat to push occupants outward against the hull. While the physics of rotation works, the human vestibular system is fiercely sensitive to it. If the radius of rotation is too small, the habitat must spin faster, unleashing severe Coriolis effects that cause crippling motion sickness and spatial disorientation. To generate one Earth gravity while keeping the rotation rate below the human tolerance threshold of 2 revolutions per minute, the spinning structure must have a radius of at least 225 meters, making the centrifuge nearly half a kilometer across. Constructing a massive rotating habitat capable of withstanding the immense structural stresses of continuous spinning for centuries adds thousands of tons to the vehicle. The bearings and rotating seals that transfer power and atmosphere between the stationary propulsion section and the spinning habitat must somehow function flawlessly, without external maintenance, for longer than any rotating seal in human history has ever survived. Even if engineers compromise and settle for partial gravity to save mass, they wander into a biological void. No experiment has ever tested multi-generational mammalian reproduction or embryonic bone formation at reduced gravity levels. The generation ship must commit to a gravity level at launch, with zero ability to correct the decision if it turns out to slowly destroy the biology of every child born in the dark. Gravity is an invisible, silent force that does not explode or irradiate, yet its absence reshapes the human species over centuries, ensuring that the people who finally reach the destination will be biologically alien to the civilization that originally sent them. Even if the structural integrity of a massive vessel holds, and the deep radiation of the void is somehow mitigated, the architecture of the cosmos forces another relentless boundary, demanding that the ship sustain its passengers biologically for the entire duration of a centuries-long voyage. This requires a flawless, endless recycling of food, water, and air without a single fraction of chemical loss. No artificial, closed, ecological life support system has ever operated successfully for more than a brief few years. In the late 1980s, researchers constructed an ambitious sealed enclosure in the American desert, spanning slightly over 3 acres, designed to harbor a miniature terrestrial ecosystem of plants, animals, insects, and humans in total isolation. It was intended to recycle all vital elements indefinitely, yet the delicate balance collapsed within its first 2 years. Oxygen concentrations plummeted to dangerous levels because the curing concrete of the structure's interior chemically absorbed the gas in a molecular interaction no engineer had anticipated. The confined insect populations crashed, completely halting agricultural pollination, which caused crop yields to plummet and left the isolated crew facing chronic hunger alongside escalating interpersonal conflict. The struggling facility ultimately had to be breached and resupplied from the outside world. Other historical attempts, such as Soviet experiments in the 1970s that relied heavily on algae cultivation and wheat farming, achieved closures of up to 180 days, but never approached the extreme complexity required for interstellar timeframes. European space agencies have studied closed-loop life support meticulously for decades, making isolated progress on waste processing and air revitalization, but they have yet to demonstrate a fully enclosed system capable of keeping even a small crew alive indefinitely. The International Space Station does not even attempt this severe level of ecological closure. It relies entirely on regular cargo deliveries carrying fresh water, oxygen, spare parts, and equipment. Without this continuous lifeline stretching up from the surface, the station would become completely uninhabitable in a matter of months. A long-duration vessel must replicate a planetary-scale system of vast oceans, atmospheric circulation, and billions of years of evolutionary tuning directly inside a pressurized metal cylinder. Every carbon atom, every water molecule, and every trace element required for basic biology must cycle endlessly through the inhabitants and the agriculture, never once accumulating in the wrong reservoir or leaking into an unusable chemical state. Sustaining the physical environment is merely a precursor to the far deeper problem of sustaining the biological lineage of the passengers trapped inside. Because propulsion limits and severe structural constraints heavily restrict the mass of the vehicle, a deep space vessel cannot carry millions of inhabitants. It would likely launch with a founding population limited to hundreds or at most a few thousand individuals. Population genetic analyses dictate that the minimum viable population required to ensure long-term survival and prevent unacceptable inbreeding sits somewhere between 500 and 5,000 people, heavily dependent on extremely strict reproductive management. Below these critical thresholds, genetic diversity steadily and inevitably erodes as generations pass in the dark. Recessive, deleterious mutations begin to pair up far more frequently, manifesting physically as reduced fertility, increased vulnerability to disease, and widespread developmental abnormalities. To prevent this slow genetic decay across centuries of isolation, natural human reproduction would likely have to be abandoned in favor of strictly managed, calculated breeding programs designed to maximize outbreeding. The population would have to rely on stored genetic material, such as sperm banks or frozen embryos, to artificially inject diversity back into the closed gene pool. Yet, cryopreservation technology has only been proven to work on timeframes measured in mere decades, not centuries. No biological sample has ever been frozen, stored in a functional state for 300 years, and successfully revived, leaving the long-term viability of these genetic reserves entirely unproven. Furthermore, implementing a compulsory, multi-generational system of reproductive control raises profound ethical dilemmas that no human society has ever successfully navigated on such a massive scale. Beyond the fragile biology of the crew lies the inevitable, grinding degradation of the machinery tasked with keeping them alive. Every physical object breaks down, and absolutely nothing constructed by human hands runs continuously for centuries without requiring external repair. While our most distant space probes have operated in some capacity for nearly half a century, they are relatively simple, largely solid-state machines. By 2026, the power output of their decaying radioactive generators had dropped so severely that engineers were forced to systematically deactivate essential heaters and scientific instruments just to keep the primary systems functioning. Within a few years, they will go completely silent, not from catastrophic destruction, but from the simple, highly predictable decay of their power sources. A crewed vessel confronts this exact reality multiplied across every single critical subsystem on board. Nuclear reactors degrade, mechanical bearings wear down, pressurized seals leak, structural materials succumb to cyclic fatigue, and electronic components accumulate irreparable radiation damage while software bugs compound over time. Moving parts like heavy pumps, atmospheric fans, fluid valves, and centrifuge joints possess strict operational lifespans measured in years or decades, never centuries. On Earth, complex machinery is maintained by vast global supply chains. A modern jet engine functions reliably for tens of thousands of flight hours because its turbine blades are regularly inspected and physically replaced with pristine parts manufactured in specialized facilities, which source raw materials mined from deep within the ground. A deep space vessel possesses absolutely none of this industrial infrastructure. It carries only what was meticulously packed at the moment of launch. If a critical water pump fails 200 years into the voyage and no spare part exists in the inventory, the life support loop breaks down permanently and the crew begins to die. Attempting to carry heavy fabrication equipment and raw material stockpiles to manufacture replacements on board adds enormous mass and spiraling complexity to a vehicle that is already mathematically strained by fundamental physics. The requirement for continuous, complex maintenance forces an even deeper crisis, moving beyond mechanics and directly into the profound instability of human sociology. Machines require highly skilled technicians to operate and repair them, meaning highly specialized technical knowledge must be transferred flawlessly from one generation to the next across centuries of total isolation. Prolonged isolation studies on Earth offer deeply grim precedents for human behavior in confined, artificial spaces. During a 520-day simulated Mars mission conducted in Moscow, carefully selected and highly motivated volunteers experienced severe sleep disruption, deep depression, and intense interpersonal conflict, with some members withdrawing completely from their required technical tasks. These subjects knew the experiment would eventually end. They possessed continuous communication with the outside world, and they were confined for fewer than 2 years. In stark contrast, the children born aboard an interstellar vessel never volunteer for the mission. They simply inherit it, growing up entirely inside a metal hull devoid of weather, horizons, or natural terrestrial landscapes, knowing with absolute certainty that they will live and die within those artificial walls. The destination their distant ancestors chose will not be reached in their lifetimes. Maintaining the psychological motivation to diligently operate complex technical systems for a goal one will never personally experience is a cognitive burden no human population has ever been asked to bear. Historical records demonstrate precisely how fragile specialized knowledge becomes when societies face disruption or isolation. After the collapse of the Western Roman Empire, the sophisticated techniques required to produce highly durable concrete vanished entirely. The precise ratios of volcanic ash, mixing methods, and careful curing processes were lost within a few generations and were not rediscovered until well over a millennium later. The Romans also engineered extraordinary aqueducts to maintain steady physical gradients over miles of terrain. But once the intricate knowledge of their maintenance faded, the structures decayed, and cities reverted to drawing water from basic wells and rain collection. The physical technology remained standing in plain sight, yet the crucial understanding of how to keep it functioning evaporated. Similarly, Pacific Islanders maintained a flawless, highly complex system of open ocean navigation for thousands of years, passing the intricate knowledge of wave patterns and stellar positions orally from master to apprentice across dozens of generations. When sudden external contact disrupted their social structures, this ancient knowledge system nearly collapsed within 3 generations, leaving only a small handful of individuals who preserved fragments of the tradition into the 20th century. Modern institutions face identical, seemingly insurmountable struggles when attempting to communicate critical information across deep time. The United States government spent decades trying to design physical warning markers for radioactive waste repositories that would remain universally comprehensible for 10,000 years. The challenge was not engineering the physical durability of the markers, but the inevitable, relentless decay of language and symbols. No human language or symbol system has ever survived unchanged across such an expanse of time, leaving panels of linguists and anthropologists to conclude that there is absolutely no guaranteed method for ensuring a message written today will be accurately understood by humans in the distant future. An isolated deep space community must somehow transmit a comprehensive technical civilization encompassing chemistry, metallurgy, medicine, agriculture, and software engineering across dozens of generations. If a single generation becomes distracted, rebellious, or politically fragmented, and fails to train enough specialists in any one of these critical fields, the vessel permanently loses the ability to maintain its own life support. Unlike on Earth, where forgotten technologies can eventually be rediscovered through cultural exchange or fresh experimentation, an isolated crew has absolutely no external source of knowledge to draw upon. What is lost inside the void stays lost forever. The onboard libraries are strictly finite, the human teachers are entirely mortal, and the students may actively reject the heavy burdens their parents attempt to place upon them. In this permanently sealed environment, the consequences of cultural decline are not merely a slow political decay. They directly result in physical death. If social cohesion fractures and opposing factions form, the losing side cannot migrate to a new territory. They remain permanently trapped inside the exact same hull, sharing the exact same air and water as their adversaries. Maintaining a unified purpose without the external pressures that traditionally renew terrestrial societies, such as trade, immigration, or environmental shifts, is a sociological requirement that remains completely unproven. The deep space vessel must sustain itself psychologically and materially longer than most historical empires have managed to persist on a planet rich with abundant resources. The human mind naturally recoils from the creeping horrors of the slow travel trap, seeking an immediate alternative when confronted with the reality that time systematically destroys biology, machinery, and social cohesion. If centuries spent drifting through the dark inevitably break everything that makes a civilization function, the seemingly obvious solution is to simply stop traveling slowly. The instinct is to compress the journey, to shorten the timeline by accelerating to a speed so extreme that the vast interstellar gulf shrinks from a span of millennia down to decades or even mere years. Reaching the destination before biological systems decay, before critical machines fracture, and before the crew forgets the original purpose of their departure feels like an airtight logical escape. Speed appears to conquer the fundamental problem of time. It is the most seductive trap the universe offers, because physics absolutely does not offer clean escapes. It only offers brutally unforgiving trades. The fast path demands a trade that is among the most punishing in all of nature, requiring travelers to exchange the slow erosion of time for an immediate cascade of physical hazards that are equally lethal. Speed solves the problem of duration by creating entirely new problems of energy and physical impact so severe that no technology currently proposed can overcome them. The very first absolute cost of speed is energy. And the price tag demanded by the cosmos is not merely large, it is profoundly incomprehensible to the human scale. In our everyday terrestrial experience, the relationship between motion and energy is straightforward, governed by classical physics, where doubling the speed of a moving object simply quadruples its kinetic energy. A standard automobile traveling at 60 miles per hour carries exactly 4 times the energy of that same automobile traveling at 30 miles per hour. This simple, comforting mathematical relationship holds beautifully for baseballs, commercial aircraft, and even our current interplanetary spacecraft moving at modest velocities. However, this elegant predictability violently breaks down as an object begins to approach the speed of light. Special relativity, which has been rigorously confirmed by over a century of continuous experimental evidence, describes exactly what happens to energy at these extreme relativistic velocities. As an object accelerates closer to the absolute limit of light speed, its effective mass increases dramatically. This does not mean the object gains more physical atoms, but rather that the amount of raw energy required to push it even slightly faster grows exponentially. The closer the vessel gets to light speed, the more energy each additional fraction of velocity demands from the engines. At 90% of the speed of light, the energy required to accelerate the object further has already grown to more than double what classical physics would predict. By the time the vessel reaches 99% of light speed, the energy requirement has climbed by a staggering factor of roughly 7. At 99.9%, the factor aggressively exceeds 22. This relationship does not scale in a linear fashion, and it never eventually levels off. It curves aggressively upward toward infinity as the velocity approaches the absolute speed of light. Translating this relativistic curvature into practical engineering terms reveals the terrifying height of the energy wall. Consider a hypothetical spacecraft with a total mass of 10,000 kilograms, which is roughly equivalent to the mass of a large commercial truck. If this truck-sized vehicle were traveling at just 10% of the speed of light, it would carry a kinetic energy of approximately 4.5 times 10 to the 18th power joules. That amount of energy equals roughly 1,000 megatons of TNT. To put that devastating yield into perspective, the largest nuclear device ever detonated by humanity, the Soviet Tsar Bomba, yielded approximately 50 megatons. Therefore, simply accelerating a single truck to 10% of the speed of light requires roughly 20 times the energy of the most powerful nuclear explosion in all of human history. Furthermore, a truck is absolutely not a crewed starship. A genuine crewed interstellar vessel, packed with heavy radiation shielding, life support systems, extensive fuel reserves, and a pressurized habitat, would possess a mass of hundreds of thousands of kilograms at the absolute minimum. When the energy equations are scaled accordingly, the resulting numbers completely abandon the realm of engineering spreadsheets and cross directly into the astrophysics of stellar bodies. Even at 10% of light speed, a velocity that still leaves Proxima Centauri over 42 years away, the energy demands are catastrophic. If mission designers want a trip time measured in single digits rather than decades, the vessel must be pushed significantly faster, and the energy wall rises accordingly. At 50% of the speed of light, the kinetic energy requirement for a 100,000 kilogram crewed vessel violently climbs to roughly 1.4 times 10 to the 21st power joules. Pushing the vessel to 90% of light speed forces that requirement up to approximately 1.2 times 10 to the 22nd power joules. These are figures that dictate the energy budgets of brilliant supernovae and massive stars, not the fuel tanks of vehicles constructed by human hands. To fully grasp the sheer scale of this limitation, one must evaluate the total global energy consumption produced by all of human civilization. In the year 2024, every single nation on Earth, operating combined, consumed approximately 5.8 times 10 to the 20th power joules of energy. This means that accelerating a modestly sized crewed vessel to 50% of light speed would require roughly 2.5 years of the total energy output from every single power plant, every combustion engine, every industrial furnace, and every chemical battery currently operating on Earth. To achieve 90% of light speed, humanity would need to pour over 20 entire years of its total planetary energy production into a single isolated vehicle. These horrific calculations strictly assume a perfect conversion of energy into forward kinetic motion with absolutely zero waste, a scenario that is completely impossible under the established laws of thermodynamics. This energy wall is a permanent fixture of reality. It does not depend on which specific propulsion technology is utilized, nor does it rely on future engineering cleverness. It is a direct, unalterable consequence of the relationship between mass, velocity, and energy as precisely defined by the universe and confirmed by every particle accelerator experiment ever conducted. Future technological advancements can change how efficiently a civilization converts raw fuel into thrust, but absolutely no amount of progress can change the raw amount of energy the universe strictly demands for a given mass to reach a given velocity. This mathematical nightmare is only the entrance fee, a calculation made before the physical rocket has even been constructed. In the year 1897, the Russian physicist Konstantin Tsiolkovsky derived a formula that continues to haunt every aerospace engineer who has followed in his footsteps. The Tsiolkovsky rocket equation elegantly describes the strict relationship between a rocket's exhaust velocity, the ratio of its fully fueled mass to its empty mass, and the maximum change in the Tsiolkovsky rocket equation elegantly describes the strict relationship between a rocket's exhaust velocity, the ratio of its fully fueled mass to its empty mass, and the maximum change in velocity it can possibly achieve. Because a rocket operates in the vacuum of space, it must carry its own reaction mass. As it burns this fuel and violently ejects the exhaust to produce forward thrust, the entire vehicle gets continuously lighter. The lighter the vehicle becomes, the more efficiently the remaining fuel can accelerate it. While this initial premise sounds like a highly beneficial cycle, the underlying mathematics reveal a brutal truth. The rocket equation dictates that the mass of fuel required to reach a specific velocity grows exponentially, not linearly. Doubling the desired final velocity does not merely double the fuel requirement, it roughly squares it. Tripling the final velocity roughly cubes the required fuel mass, because the vehicle must carry the fuel it needs for the end of the burn at the very beginning of the journey. It requires fuel simply to accelerate the unburned fuel, and more fuel to accelerate that fuel, creating a recursive chain of mass that aggressively spirals out of control. Reaching interstellar speeds forces these mass ratios to become so heavily extreme that they completely leave physical reality behind. Conventional chemical rockets, the highly reliable engines that carried humanity into the space age, produce exhaust velocities ranging from 3 to 5 kilometers per second. If engineers attempted to use chemical propulsion to reach even 1% of the speed of light, which is roughly 3,000 kilometers per second, the mass ratio required would be mathematically absurd. The amount of highly combustible fuel required would heavily exceed the entire mass of the observable universe by many consecutive orders of magnitude. It is a direct, undisputed calculation proving that chemical rockets absolutely cannot reach interstellar speeds. The mathematics forbid the attempt with absolute finality. More advanced concepts, such as nuclear thermal rockets, improve the exhaust velocity to roughly 8 to 9 kilometers per second. Yet the mass ratio remains far too high for meaningful interstellar velocities. Ion engines can push exhaust velocities to 30 or 50 kilometers per second, which is significantly better, but still completely insufficient for a massive crewed deep space mission. Theoretical fusion rockets, which remain unbuilt, might eventually achieve exhaust velocities of several hundred, perhaps up to 700 kilometers per second. This finally brings the necessary mass ratio down into a range where interstellar travel becomes mathematically conceivable on paper, but the rocket equation continues to ruthlessly punish the attempt. At the highly optimistic limit of 700 kilometers per second, a 150-ton spacecraft attempting to reach 8% of light speed would require a mass ratio so staggeringly extreme that the initial fuel load would outweigh the final payload by a factor of nearly 10 to the 15th power. That equates to a quadrillion kilograms of highly volatile fuel required for every single kilogram of the actual ship. If the fusion exhaust velocity drops even slightly below that optimistic projection, the required fuel mass climbs by additional orders of magnitude, rapidly demanding fuel reserves that completely dwarf the mass of entire star systems. Published analyses heavily confirm that even highly advanced nuclear fusion cannot safely power large crewed vehicles to star-crossing speeds without encountering this recursive trap. Only one theoretical fuel source in the known universe possesses enough raw energy density to fundamentally break the tyranny of the rocket equation: antimatter. When a particle of ordinary matter collides with its exact antiparticle, both pieces of matter annihilate completely, perfectly converting nearly 100% of their combined mass into pure energy. This violent physical process is roughly 3 orders of magnitude more efficient than nuclear fusion and roughly 10 orders of magnitude more efficient than standard chemical combustion. An antimatter-powered rocket could, in theoretical physics, finally achieve the highly favorable mass ratios that make interstellar velocities genuinely reachable with a reasonably sized spacecraft structure. The fatal flaw in this scenario is that antimatter exists almost entirely as a theoretical construct when discussed as a viable industrial fuel source. In raw, practical terms, the total amount of antimatter ever successfully produced by humanity across every single particle accelerator on Earth over several decades of continuous operation amounts to less than 10 nanograms. The European Organization for Nuclear Research, operating the only facility in the world with a dedicated antimatter production program, reported in 2025 that its latest, most advanced techniques allow the production of roughly 15,000 anti-hydrogen atoms over a span of several hours. While this was hailed as a massive scientific breakthrough that researchers previously considered complete science fiction, 15,000 atoms weigh roughly 25 times 10 to the negative 21st power grams. To properly fuel even a modest, crude interstellar spacecraft, engineers would require hundreds of grams or even hundreds of kilograms of stable antimatter. The staggering gap between current production rates and actual mission requirements spans more than 20 complete orders of magnitude. It is the volumetric difference between a single microscopic raindrop and all the combined water in the Pacific Ocean. Even if a future civilization somehow generated the titanic planetary power required to manufacture antimatter in industrial bulk, the substance remains extraordinarily difficult to physically store. Because antimatter violently annihilates upon physical contact with any ordinary matter, it cannot be kept in a physical tank. It must be perfectly suspended in a flawless vacuum using highly complex, incredibly stable electromagnetic fields. If the magnetic containment field fails for even a fraction of a second, the resulting uncontrolled annihilation would instantly vaporize the entire vessel. No storage system capable of safely holding macroscopic, kilogram quantities of antimatter for the decades-long duration of an interstellar mission has ever been constructed, nor has one been convincingly designed in engineering literature. The immense challenges involved are not merely incremental improvements on existing battery or fuel tank technology. They represent completely unsolved problems deep within fundamental physics. The energy wall stands completely reinforced by the sheer brutality of the rocket equation. No existing, near-future, or highly theoretical propulsion system can successfully accelerate a heavy crewed spacecraft to relativistic interstellar velocities without demanding either mathematically impossible quantities of conventional fuel or a highly exotic energy source that human civilization fundamentally cannot produce in usable amounts. The physics are devastatingly clear, and the mathematics are entirely settled. The barrier to fast travel is not a lack of human imagination or engineering courage. It is the absolute, unyielding relationship between mass, energy, and velocity exactly as the universe has structurally defined it. Suppose, for the sake of deep exploration, that a future civilization somehow solves the seemingly insurmountable energy problem permanently. Suppose they construct a fusion reactor of unimaginable power, or they learn to mathematically stabilize and manufacture antimatter in massive industrial bulk, or they develop some entirely novel propulsion system that current physics cannot yet predict. Suppose they successfully accelerate a massive crewed vessel to 10 or 20% of the speed of light, sending it hurtling toward another star system to escape the biological decay of a slow journey. In doing so, they have fundamentally transformed the interstellar medium from an empty, passive void into a relentless hailstorm of physical destruction. The space between the stars is heavily romanticized in human thought as a perfect, silent vacuum, but it is not truly empty. It contains approximately 1 hydrogen atom per cubic centimeter on average, drifting aimlessly alongside occasional helium atoms, trace heavier elements, and microscopic dust grains. At the modest speeds humanity currently achieves with conventional chemical rockets, this incredibly sparse material is entirely irrelevant to structural engineering. Voyager 1 has been steadily plowing through this exact medium for decades with absolutely no measurable physical effect on its fragile hull. At 10 kilometers per second, or even 100 kilometers per second, the interstellar medium functions essentially as nothing. However, at 10% of the speed of light, that exact same medium becomes something else entirely, shifting from a passive environment to an active threat. The universe does not actually need to place massive physical obstacles in the path between stars to prevent a crossing. It only needs to scatter a few invisible atoms and stray grains of dust per cubic centimeter across the void, and the unforgiving physics of extreme speed will accomplish the rest of the destruction. A single interstellar dust grain with a mass of just 1 milligram, an object smaller than a typical grain of sand, and thinner even than the width of a human hair, carries a kinetic energy of approximately 450 million joules when it violently strikes a physical surface, moving at 10% of the speed of light. To place that mathematical figure into a terrestrial context, a heavy bullet fired directly from a .357 Magnum handgun delivers roughly 720 joules of energy upon impact. The microscopic dust grain, therefore, strikes the spacecraft with the combined physical force of over 600,000 Magnum bullets arriving simultaneously at one single microscopic point on the hull. This physical event is absolutely not a simple collision in the traditional mechanical sense. It is a rapid, catastrophic detonation. Both the offending dust grain and the specific surface area it strikes instantly vaporize into superheated plasma under the extreme transfer of kinetic energy. A deep crater rapidly forms in the structural armor, and molten material violently sprays outward into the freezing vacuum. The physical impact is entirely equivalent to a small conventional bomb detonating directly against the exterior of the ship. Extensive research conducted at the Lawrence Livermore National Laboratory aimed specifically at modeling the complex effects of interstellar dust on relativistic spacecraft calculated the cumulative damage of these impacts over time. They determined that, over a highly optimistic 4-light-year journey at 20% of light speed, the continuous barrage of dust impacts could deeply erode, melt, or completely vaporize more than 0.5 millimeter of a dense quartz surface across the entire forward-facing area of the vehicle. Furthermore, recent complex modeling published in the Astrophysical Journal meticulously examined the interaction of relativistic spacecraft with the interstellar medium in much finer physical detail. The published results rigorously confirmed that even for extremely small, gram-scale robotic probes, the relentless dust grain impacts at 20% of light speed significantly modify the underlying material structure through rapid melting, while the continuous gas atom bombardment steadily heats the leading surface to significant equilibrium temperatures. Dissipating this extreme heat in the vacuum of space presents yet another massive engineering challenge, but the physical impacts remain the primary threat. If the vessel attempts to push even faster to further shorten the journey, moving at 50% of light speed, the kinetic energy of each individual grain impact scales violently upward by roughly a full order of magnitude. At that extreme velocity, a single 1 milligram grain delivers raw, destructive energy completely comparable to a large conventional explosive bomb. Furthermore, microscopic dust grains are absolutely not the only physical hazards floating silently in the dark. The interstellar medium also contains frozen ice fragments, micropebbles, and rogue debris of highly unknown composition and size distribution, falling somewhere between the scale of micron-sized dust and small dark asteroids. The precise size spectrum of solid material drifting in deep interstellar space remains poorly characterized, simply because detecting isolated, cold objects smaller than a star from light years away is functionally impossible with any current astronomical technology. A massive ship, traveling at half the speed of light for an entire decade, physically sweeps out a cylindrical volume of space so staggeringly large that encountering an object far more massive than a simple dust grain becomes highly statistically plausible. A single, unfortunate impact from a pebble-sized object at that relativistic velocity would suddenly release energy entirely equivalent to a tactical nuclear weapon, instantly vaporizing the vessel and ending the mission without any warning. Engineering an effective defense against these catastrophic relativistic impacts is theoretically possible on paper, but it proves practically devastating to the overall mission design. One prominent engineering proposal suggests deploying a massive forward-mounted sacrificial shield to protect the crew. This would be an enormously thick plate of expendable, highly dense material positioned physically ahead of the main ship, designed specifically to absorb the kinetic energy and slowly vaporize under the incoming impacts. The shield slowly erodes over the decades or centuries of the journey, gradually sacrificing its own mass so that the fragile habitat survives safely behind it. However, this shield must be enormously thick and incredibly dense to successfully withstand the cumulative kinetic energy of billions of high-speed hydrogen atom impacts and thousands of detonating dust grain strikes. Its massive dead weight adds directly to the overall fuel budget, which is already strained to the absolute breaking point by the relativistic energy wall. Every single kilogram of heavy shielding requires additional fuel simply to accelerate it, which in turn requires even more additional fuel to accelerate that initial fuel. This cruel mechanical reality spirals violently upward through the exponential cruelty of the rocket equation, rapidly demanding impossible masses of propellant just to push the protective armor. Another highly theoretical defensive proposal involves utilizing an electromagnetic deflector. This complex concept relies on projecting a phenomenally powerful magnetic field far ahead of the physical ship to forcefully ionize incoming particles and sweep them safely aside into the void before they can strike the hull. While this elegant concept works in strict principle for electrically charged particles, it completely fails to deflect neutral atoms, neutral dust grains, and any macroscopic physical debris that naturally carries no magnetic charge. Furthermore, it requires an enormous, continuous supply of electrical power to generate and meticulously maintain a magnetic field strong enough to noticeably alter the trajectory of heavy particles arriving at a significant fraction of the speed of light. This staggering continuous power requirement competes directly with the extreme energy desperately needed for the primary propulsion systems, creating yet another unresolvable engineering paradox. Even if the vessel somehow manages to survive the physical bombardment of dust and microscopic pebbles through impossibly thick armor, the most pervasive element of the interstellar medium creates an invisible, inescapable nightmare for the biology of the crew. Dust is absolutely not the only thing the interstellar medium does to a fast-moving ship. The solitary hydrogen atoms themselves become highly lethal weapons of radiation. At rest, a single hydrogen atom floating in interstellar space is completely harmless to living tissue. It drifts invisibly, carrying negligible kinetic energy and posing zero threat to any biological organism or electronic circuit. However, in the physical reference frame of a spacecraft moving at a highly significant fraction of the speed of light, every single hydrogen atom in the vast path ahead is approaching the ship at that exact same relativistic fraction of light speed. The kinetic energy of the atom, measured strictly from the ship-us frame of reference, grows aggressively with velocity according to the exact same relativistic equations that strictly govern the ship-us own forward motion. At just 10% of the speed of light, each individual hydrogen atom strikes the forward hull with an energy of roughly 5 mega-electron volts. That highly specific energy level is completely comparable to the destructive energy of particles intentionally used in targeted medical radiation therapy to destroy cancerous tissues on Earth. If the ship successfully accelerates to 50% of light speed, the energy per impacting atom aggressively climbs to nearly 150 mega-electron volts. At 90% of light speed, it firmly enters the giga-electron volt range, making the impact completely comparable to the devastating particles generated in high-energy accelerator experiments. The entire forward-facing surface of the ship consequently experiences a continuous, unbroken bombardment of hydrogen and helium nuclei, arriving at energies entirely equivalent to a massive particle accelerator beam aimed directly, continuously at the hull. This highly lethal radiation bombardment does not come from a distant, isolated cosmic source like a distant supernova that thick shielding can simply absorb and block. It is generated entirely by the ship's own extreme forward motion. The faster the ship travels, the more energetic and deeply penetrating the atomic bombardment inevitably becomes. The ship is literally creating its own inescapable radiation storm merely by moving rapidly through a sparse medium that would be completely harmless if the ship were stationary. This forward-directed radiation easily penetrates conventional physical shielding. Deep inside the hull materials, it triggers violent secondary particle showers through the exact same physical process of spallation that makes standard galactic cosmic ray shielding so incredibly difficult to design for slower generation ships. It systematically damages delicate onboard electronics, degrades the structural integrity of the hull materials over time, and exposes the biological crew to lethal radiation doses that grow relentlessly with the square of the ship's US velocity. A crewed ship traveling at 50% of light speed experiences a forward-directed radiation flux so intensely powerful that it would deliver absolutely lethal biological doses to an unshielded crew in a matter of mere days. The tragic irony of this physics is profound and completely inescapable. The ship-us extreme speed, the exact mechanism that was desperately supposed to save the biological crew from the slow travel problem of cumulative radiation exposure over centuries, becomes itself the absolute dominant source of immediate, lethal radiation. The interstellar medium at rest is a vacuum so completely perfect that highly advanced laboratories on Earth cannot even match it. At relativistic speeds, that exact same perfect vacuum violently becomes a weapon aimed directly at the traveler. The universe strictly dictates that speed turns empty space itself into a hailstorm of destructive energy. There is another profound physical constraint that intimately connects the monstrous energy wall directly to the fragile biology of the human body, governing exactly how quickly a spacecraft can actually reach these theoretical interstellar speeds, even if the energy problem is miraculously solved by future generations. That strict constraint is acceleration tolerance. The human body possesses the capacity to survive very brief, violent bursts of extreme acceleration. Military fighter pilots can successfully endure 7 to 9 times the force of normal Earth gravity during aggressive aerial maneuvers, though they require highly specialized pressure suits, intense physical training, and they can only sustain those crushing forces for mere seconds before risking visual blackout or severe physical injury. Sustained, continuous acceleration over long durations is a fundamentally different matter entirely. At exactly 1 Earth gravity, which is the natural acceleration due to the gravitational pull of our home planet, a person feels exactly as heavy as they feel standing completely still on the ground. This specific level of force is entirely comfortable, indefinitely survivable for human physiology, and is universally considered by aerospace medicine to be the absolute upper limit for sustained acceleration on a crewed interstellar mission. Any higher sustained acceleration would physically require the crew to endure the highly oppressive sensation of weighing significantly more than normal for unbroken weeks, months, or even years in the dark. At a sustained force of 2 Earth gravities, a typical 70-kilogram person feels as though they weigh 140 kilograms. Under this continuous heavy load, every single physical movement becomes deeply exhausting, and the cardiovascular system heavily strains to pump blood upward against the increased resistance. Sleeping becomes intensely difficult, and at a sustained 3 Earth gravities or above, the prolonged physical exposure directly causes irreversible tissue damage, severely impaired blood circulation, and eventually catastrophic organ failure. Sustained acceleration significantly above 1 Earth gravity for anything more than brief, isolated periods is not an engineering design choice. It is an absolute medical impossibility for any crewed vessel. At exactly 1 Earth gravity of sustained forward acceleration, the timeline for reaching necessary interstellar velocities is rigidly fixed by the unyielding laws of physics. It takes approximately 35 days of continuous engine thrust just to reach 10% of the speed of light. It requires roughly 200 days, nearly 7 full months, of constant acceleration to reach 50% of light speed. To reach 77% of the speed of light, the engines must fire continuously for approximately 1 full year. These specific timeframes are entirely non-negotiable scales, strictly determined by the mathematical relationship between physical acceleration and velocity, heavily bound by the human body's inability to safely tolerate higher gravitational forces without sustaining fatal biological damage. During this entire protracted acceleration phase, the ship's primary engines must fire continuously without a single interruption. Every single second of active thrust aggressively consumes raw fuel. Every kilogram of fuel consumed during this long acceleration period is a kilogram that was already accelerated along with the main ship during all the preceding seconds of the flight. meaning it already consumed fuel simply to get that unburned fuel up to the current speed. The rocket equation fiercely punishes these long engine burn times with devastating exponential fuel costs. A 35-day continuous engine burn just to reach 10% of light speed is vastly more expensive in terms of required fuel than an instantaneous, impossible acceleration to that exact same final velocity would be. This mathematical penalty occurs not because the final speed fundamentally differs, but because the heavy fuel must be continuously carried and forcefully accelerated along with the payload for the entire 35-day duration. Lowering the rate of acceleration to reduce crew discomfort simply extends the total burn time and drastically increases overall fuel consumption. Raising the rate of acceleration to save precious fuel physically injures or kills the crew. There is absolutely no favorable physical trade in either direction. The frail human body firmly sets a hard ceiling on allowable acceleration, and the rocket equation brutally penalizes the long, continuous burns that this low biological ceiling requires. These two unyielding constraints silently squeeze the mission design from completely opposite sides. Furthermore, this long acceleration phase is the period of greatest physical vulnerability to the lethal interstellar medium. During the initial weeks or months of continuous thrust, the ship is steadily accelerating through a critical velocity range where physical impacts from ambient dust and gas are becoming increasingly exponentially dangerous. But the ship has not yet reached its final cruising speed. It is simply too slow to benefit from any time compression effects of high relativistic velocity. Yet it is fast enough for microscopic impacts to cause catastrophic structural damage. It is burning its limited fuel reserves at enormous, terrifying rates, and it absolutely cannot maneuver laterally to avoid incoming physical obstacles because any sideways thrust violently disrupts the carefully calculated acceleration profile and fatally wastes fuel. The inevitable deceleration phase completely compounds every single one of these severe physical constraints. A 35-day acceleration period at 1 Earth gravity mathematically demands a 35-day deceleration period at the final destination. 6 months of continuous thrust speeding up strictly dictates 6 months of continuous thrust slowing down. The exact same physical vulnerability to the deadly interstellar medium that severely plagued the acceleration phase violently returns during the braking maneuver. But this time, the ship is actively decelerating nose first directly into the unknown debris field of a new star system, rather than accelerating safely away from a previously cleared launch corridor in our own solar system. Moreover, the ship will have endured the entire decades-long coasting phase carrying the massive dead weight of all its deceleration fuel. This incredibly heavy fuel significantly added to the ship's total mass during the initial acceleration, deeply worsening the fuel requirements on the way out. But it served absolutely no functional purpose until the exact moment of arrival. The interstellar medium severely punishes every single second spent at these intermediate cruising velocities, and every single kilogram of required shielding structure and heavy deceleration fuel feeds directly back into the initial mass that must be accelerated in the first place. This specific acceleration constraint is never a secondary design consideration. It is a massive structural barrier that interacts directly and violently with every other single barrier in the chain. The metallic links hold firm. And after the vast planetary energy has been spent, after the kinetic dust detonations have been miraculously survived, after the blinding radiation storms have been endured, one more physical barrier patiently waits. The massive ship must physically stop. Accelerating a heavy mass to deep interstellar speeds successfully consumes monstrous civilization-scale quantities of energy. Decelerating that exact same mass from those extreme speeds forcefully consumes exactly the same amount of energy. A speeding interstellar ship that fundamentally cannot decelerate simply does not genuinely arrive at its final destination. It performs a frantic, useless flyby, screaming past the target star system at a highly significant fraction of the speed of light, possessing only a few brief minutes or scattered hours to collect optical data before the target star system falls completely behind them, lost forever into the dark void. For a highly expendable robotic probe, this rapid flyby might be deemed scientifically acceptable. For a deeply invested crewed mission, it is profoundly absurd. The human crew absolutely must slow down, successfully enter a stable planetary orbit, and presumably establish some permanent physical presence at the alien destination. Achieving this successfully dictates carrying enough onboard fuel or raw energy to perfectly reverse the entire immense velocity accumulated during the incredibly long outbound trip. This unavoidable deceleration problem effectively doubles the total raw energy requirement for any crewed interstellar mission. If safely accelerating the mass to 10% of light speed firmly requires the total energy equivalent of one entire year US global output on Earth, then properly decelerating from that exact speed directly requires another full year US worth of total planetary energy. The staggering fuel budget completely doubles, the initial mass doubles, and the heavy fuel strictly needed to carry that extra heavy fuel doubles again in a vicious mathematical cycle. The rocket equation use brutal exponential penalty applies equally and fully to both distinct halves of the long trip independently. This effectively means the combined mass ratio for a complete accelerate and decelerate mission profile is roughly the mathematical square of the massive mass ratio required for the acceleration phase alone. Some theoretical engineering proposals attempt to cleverly dodge this massive deceleration fuel problem. The concept of a magnetic sail, or mag sail, suggests utilizing the ambient interstellar medium itself as a physical braking mechanism, deploying a vast, incredibly powerful magnetic field to deliberately create intense physical drag against the incredibly thin gas drifting between the stars. While this specific concept is theoretically sound in pure physics, it strictly requires deploying a magnetic field spanning many kilometers in diameter, relying entirely on heavy superconducting coils that must somehow perfectly function after decades of enduring relentless relativistic radiation bombardment in deep space. Other theoretical proposals strongly suggest using the destination star's own light pressure to slowly break a massive light sail. However, this subtle mechanism works mathematically only for extremely light, highly delicate robotic probes, absolutely not for massive, heavily armored crewed vessels. Standing tall and unyielding behind all of these interconnected barriers is the final, absolute boundary. The one that can never be creatively engineered around, patiently waited out, or eventually solved by some undefined future technology. The speed of light is an absolute physical limit imposed by the universe. Special relativity does not merely make faster than light travel extremely difficult for engineers. It makes it fundamentally, mathematically impossible for any object possessing mass. As any massive physical object closely approaches the speed of light, the total amount of energy strictly required to accelerate it any further aggressively approaches absolute infinity. This is not simply a very large, inconvenient number. It is not a distant numerical target that a sufficiently advanced futuristic civilization might eventually somehow reach through technological prowess. It is actual mathematical infinity. The speed of light is completely unlike a terrestrial highway speed limit, which is merely an arbitrary number that can be easily exceeded if one possesses sufficient engine power and a willingness to blindly accept the resulting penalties. It is, instead, a fundamental, unchangeable structural feature of spacetime itself. The precise physical nature of mass, the behavior of energy, and the fundamental geometry of the entire universe heavily conspire to absolutely ensure that no material object can ever reach, let alone slightly exceed, exactly 299,792,458 meters per second. This severe restriction has been rigorously confirmed by every single particle accelerator experiment throughout human history. The Large Hadron Collider, operated by the European Organization for Nuclear Research, routinely accelerates subatomic protons to more than 99.9999% of the absolute speed of light. At that extreme, mind-bending velocity, each tiny individual proton carries the staggering kinetic energy of a macroscopic flying mosquito. This occurs not because the subatomic proton is physically massive, but because it has been violently accelerated so incredibly close to the absolute universal limit that its effective relativistic energy has grown by an astonishing factor of roughly 7,000 beyond its normal resting mass energy. Attempting to push those tiny protons even slightly faster fiercely requires disproportionately more massive amounts of energy. Successfully reaching exactly 100% of light speed would mathematically demand infinite energy. This specific boundary is entirely not a theoretical scientific prediction awaiting future experimental confirmation. It is a firmly observed fact, rigorously measured and repeatedly verified in massive laboratories every single day. Even if a ship could travel at 99% of light speed, the physical universe remains staggeringly, terrifyingly large. Proxima Centauri would still be 4.3 years away at that extreme velocity. The dense center of our own galaxy would still remain over 26,000 years away. The nearest large galaxy, Andromeda, would still be over 2.5 million years away. Time dilation at these extreme relativistic speeds heavily compresses the perceived journey strictly from the traveler, us internal perspective, meaning a small crew successfully traveling at 99% of light speed would physically experience roughly 1/7 the elapsed time compared to completely stationary observers firmly on Earth. However, they must still successfully accelerate to that terrifying speed, violently survive the interstellar medium at that speed, and properly decelerate at the distant destination. Each and every one of those crucial steps violently encounters every single lethal barrier already described, aggressively amplified by the extreme relativistic velocity. Time dilation is very frequently presented in popular thought as a profound gift that relativity graciously offers to ambitious interstellar travelers. The faster the vessel travels, the much slower time visibly passes aboard the enclosed ship relative to normal clocks synchronized on Earth. At 90% of light speed, the traveling crew physically experiences time at roughly 44% of the normal terrestrial rate. A journey that firmly takes 10 full years from Earth, us external perspective, feels exactly like only 4.5 years aboard the isolated ship. At 99% of light speed, this ratio compresses even further. The crew physically ages roughly 1 single year for every 7 years that pass completely on Earth. At 99.9%, the temporal compression vastly exceeds a ratio of 20:1. In pure mathematical principle, a heavily shielded crew traveling fast enough could rapidly cross enormous cosmic distances strictly within a single subjective lifetime, while deep centuries or heavy millennia pass silently in the vast universe around them. While this specific phenomenon deeply sounds like an elegant solution to the slow travel trap, it is actually a deeply tragic, hidden barrier. It is a barrier that fundamentally severs the deep space mission completely from the civilization that originally launched it, doing so in profound ways that simple communication delay alone absolutely cannot. Consider deeply the structural implications of a crewed mission directed to a star system firmly located 40 light-years away, traveling at a steady 95% of light speed. From Earth, as completely stationary frame of reference, this massive journey takes approximately 42 years each individual way. However, strictly from the traveling crew as frame of reference, time dilation heavily compresses the brutal trip to roughly 13 subjective years each way. If the crew formally departs Earth in the specific year 2200, they successfully arrive at the alien destination around the year 2242 by Earth's official calendar. Feeling intensely as though only 13 short years have completely passed for them biologically, they spend one single year actively exploring the system and firmly depart for home. They violently arrive back at Earth around the year 2285 by Earth's calendar. A full 85 years have deeply passed on Earth. Roughly 27 years have passed for the isolated crew. The small crew returns directly to a world that has fully experienced nearly a complete century of deep history they absolutely did not witness. The individuals who proudly launched the mission are completely dead. Their direct children are either incredibly elderly or also dead. The vast political systems, complex languages, technological frameworks, and cultural references of the year 2285 bear almost absolutely no resemblance to those they intimately knew in 2200. The highly trained crew rigorously prepared for a specific mission designed by a civilization that completely no longer exists in the exact form they originally knew it. They physically return as total strangers to a deeply alien world that has completely moved on without them. This severe disconnection is entirely not a simple psychological footnote. It is a massive structural problem for all mission design. It firmly demands asking who exactly funds a colossal mission whose scientific results will absolutely not return for 85 years. Who specifically trains a crew, intimately knowing that every single person they deeply love will be completely dead long before the mission is even half over? Who meticulously maintains the deep ground infrastructure, the massive communication arrays, the critical institutional knowledge, and the fragile political will to actively support a silent mission across nearly a full century of elapsed Earth time? The mission fundamentally requires strict continuity of purpose across a span far longer than most historical governments have ever successfully lasted. And this deep asymmetry runs even deeper than earthly politics. Critical messages sent directly from the moving ship during the long journey arrive at Earth heavily time-dilated as well. The isolated crew-us weak transmissions are deeply redshifted, stretched to drastically longer wavelengths strictly by their extreme relativistic velocity. The overall data rates severely drop. The complex information becomes incredibly harder to reliably decode, and the specific content of the messages strictly refers to an outdated mission context that is aging entirely differently than the evolving context firmly on Earth. The crew proudly sends a detailed report in what feels exactly like year 5 of their specific mission. It faintly arrives at Earth many decades after the initial launch. The original scientists who designed the specific instruments described in the report have fully retired. The essential software that effectively processes the specific data format has been entirely superseded 3 separate times. The massive terrestrial institutions that were supposedly supposed to receive and deeply analyze the data have been reorganized, completely merged, or entirely dissolved. Time dilation completely fails to eliminate the severe cost of interstellar travel. It simply shifts the tragic cost entirely from the travelers to absolutely everyone they left behind in the dark. The crew ages slowly, but the civilization they serve ages at the completely normal, relentless rate. The vast, unbridgeable gap between them silently grows with every single passing year, precisely measured in one frame and felt deeply in both. If the entire grand purpose of deep interstellar travel is to greatly extend human civilization, as profound reach, time dilation completely undermines that very purpose by permanently disconnecting the solitary travelers from the specific species they supposedly represent. They tragically become temporal exiles, moving silently through the dark universe at a completely different rate than the rest of humanity. Furthermore, time dilation only truly becomes mathematically significant at extreme velocities that violently trigger every single other lethal barrier in the entire chain. One absolutely does not get meaningful time compression below roughly 50% of light speed. At 50%, the physical dilation factor is only about 13%, barely noticeable to human perception. The deep compression that actually mathematically matters for interstellar journey planning, massive factors of 2 or 5 or 10, rigorously requires extreme velocities firmly above 90% of light speed. These are precisely the extreme velocities where microscopic dust grains violently detonate against the hull, where solitary hydrogen atoms instantly become a deadly, forward-directed radiation storm, where the immense energy budget vastly exceeds the total output of entire civilizations, and where deceleration completely doubles every single catastrophic cost. Time dilation is absolutely not a convenient loophole magically hidden in the barrier. It is a structural feature that strictly becomes available only at velocities where every single other physical barrier is at its absolute, most severe breaking point. There is a deeply unsettling assumption embedded within every proposal for crossing the interstellar void, a profound blind spot that relies entirely on the fragile nature of long-distance observation. The entire justification for enduring centuries of biological decay on a generation ship, or braving the catastrophic kinetic bombardments of a relativistic journey, fundamentally depends on knowing with absolute certainty that a habitable world is waiting at the end of the deeply traumatic crossing. This critical knowledge currently comes strictly from optical and infrared telescopes. Astronomers meticulously observe a distant star, successfully detect a planetary body orbiting within the narrow habitable zone, carefully analyze the spectrum of starlight filtering through its atmosphere, and carefully infer local conditions that might theoretically support human biology. These astronomical observations are completely real and are becoming increasingly precise with modern instruments. The James Webb Space Telescope currently possesses the capability to identify the specific chemical composition of exoplanet atmospheres from distances measured in light years, actively detecting carbon dioxide, water vapor, methane, and oxygen, which are the highly sought-after chemical signatures of a world that might potentially be habitable. However, optical inference is absolutely not physical confirmation. A chemical spectrum strictly dictates which specific molecules currently float in the upper atmosphere. It absolutely does not tell an observer whether the planetary surface below is solid rock or completely molten. It does not reveal the severe acidity of the distant oceans, the heavy chemical toxicity of the alien soil, or the hidden presence of a completely alien microbiology that might prove instantly lethal to all Earth-based organisms. Furthermore, it completely fails to describe the radioactive environment on the surface, the frequency of catastrophic volcanic eruptions, the deep stability of the climate over long centuries, or whether the massive tidal forces originating from the host star have permanently locked the planet's rotation, causing one distinct hemisphere to violently bake in permanent daylight while the other permanently freezes in eternal darkness. Many of the most highly promising habitable zone exoplanets currently identified orbit small, volatile red dwarf stars. These specific stars are fiercely prone to highly violent stellar flares that possess enough raw power to completely strip a neighboring planet's entire atmosphere away into the void. Telescopic data can only cautiously suggest that a distant planet might be habitable. It fundamentally cannot guarantee that a planet is genuinely habitable for human beings. That definitive physical determination strictly requires an observer being physically present on the surface. An interstellar vessel simply cannot hedge this enormous gamble. It carries absolutely no extra fuel to casually alter course toward a second backup destination. It absolutely cannot turn around and safely return to Earth. The precise trajectory is plotted completely centuries in advance, rigorously aimed toward one single star system, and the isolated passengers are permanently committed to that exact trajectory from the very second the launch clamps release. If the chosen planet tragically turns out to be entirely uninhabitable upon arrival, the monumental mission does not fail gracefully. It fails absolutely and permanently. Centuries of desperate survival, of heavy radiation endured, of failing machines endlessly maintained, of isolated generations born and buried completely in transit, firmly end not in scientific triumph, but in total physical extinction directly at the finish line. The exhausted crew violently arrives at a hostile world that absolutely cannot sustain them, and they possess absolutely no physical means of going anywhere else in the cosmos. This profound risk is absolutely not a hypothetical thought experiment. The entire history of our own local planetary science is a sobering history of optimistic expectations being violently overturned by direct physical observation. Before physical spacecraft visited the planet Venus, many leading scientists confidently expected a warm, wonderfully wet world thriving beneath its thick clouds. The direct physical reality proved to be a completely hostile surface, hot enough to instantly melt lead, suffocating under an immensely crushing atmosphere of heavy carbon dioxide and highly corrosive sulfuric acid. Before robotic rovers successfully landed on Mars, numerous scientific models optimistically predicted accessible subsurface water near the surface. The physical reality has consistently proven vastly more arid, frozen, and deeply hostile than any optimistic projections ever initially suggested. Every single planet and moon that physical spacecraft have visited within our own relatively small solar system turned out to be completely different from what optical telescopes alone originally predicted, often radically and lethally different. There is absolutely no logical reason to expect that complex exoplanets sitting 4 or 40 light-years away will match their distant spectral portraits any more faithfully. Furthermore, planetary conditions actively change over time. A distant planet that was marginally habitable when carefully observed from Earth may completely cease to be habitable by the time the massive ship finally arrives, long centuries later. Violent stellar flares, extended volcanic winters, subtle orbital perturbations, and slow atmospheric escape are highly dynamic physical processes. These processes relentlessly operate on vast timescales that heavily overlap with the extended duration of a slow interstellar journey. The specific world the terrestrial astronomers originally saw is strictly the world exactly as it existed when the light originally left it, 4 or 40 years before the massive ship even launched. By the precise time the heavily degraded ship physically arrives, the alien planet has been actively evolving in the dark for deep centuries entirely beyond the last possible optical observation. The desperate crew is literally traveling toward an obsolete photograph, absolutely not a fixed place, and that specific photograph may be completely scientifically obsolete long before they are even halfway there. This terrifying arrival problem completely closes a vicious circle that ambitious engineering concepts would heavily prefer to leave deliberately open. The entire philosophical justification for demanding that human beings endure centuries of extreme physical hardship is that something genuinely worthwhile patiently waits at the absolute end. If that specific something fundamentally cannot be guaranteed, and physical reality dictates that it absolutely cannot, then the deep space mission asks its trapped passengers to blindly accept every single lethal risk previously described in exchange for a destination that may simply kill them immediately upon arrival. The original passengers who passionately launched the ship made that fatal bargain voluntarily. Their distant descendants, born completely without choice into the enclosed mission, had absolutely no say, and the completely hostile planet they ultimately arrive at may rapidly render the entire multi-generational sacrifice entirely meaningless. When one deeply examines the full architecture of these physical barriers, a terrifyingly perfect, unresolvable loop reveals itself. Every single proposed engineering solution to one specific problem immediately and violently worsens another. If engineers add massive physical shielding to successfully survive the relentless dust impacts of relativistic travel, they aggressively increase the total mass of the vessel. In total mass mathematically forces an exponential increase in the fuel requirements governed by the rocket equation, which in turn violently pushes the overall energy demands further toward the physically impossible. If engineers intentionally increase the vessel US speed to drastically shorten the biological radiation exposure time of the crew, they mathematically increase the exact kinetic energy of every single solitary hydrogen atom striking the forward hull, which ironically and catastrophically increases the lethal radiation dose delivered per second. If the designers responsibly force the ship to carry sufficient fuel for the absolutely necessary deceleration phase at the destination, they completely double the immense mass that must be forcefully accelerated in the first place, strictly doubling the civilization-breaking energy requirement for the outbound trip. Building a significantly larger ship to safely carry more thick shielding, vastly more fuel, and absolutely necessary redundant life support systems simply increases the total structural mass that must be violently pushed to interstellar velocity, rapidly feeding the exponential loop of impossibility. Every single proposed solution is a heavy physical cost. Every heavy cost rapidly becomes a completely new barrier. Every single barrier links directly back to the others in a perfectly closed, escalating loop of impossible physical demands. In the harsh architecture of the cosmos, there is absolutely no free variable. There is completely no engineering parameter that can be safely adjusted without immediately tightening a lethal constraint somewhere else in the exact same system. The universe absolutely does not offer a path through the void. It exclusively offers an interlocking chain, and every single link is flawlessly welded to the next. The slow path of the generation ship completely fails because deep time systematically destroys everything biological, mechanical, and human. The fast path of the relativistic vessel completely fails because extreme speed violently turns empty space itself, the solitary atoms of hydrogen drifting harmlessly between the ancient stars, and the microscopic grains of dust that have floated completely undisturbed in the silent void for millions of years, into highly devastating instruments of destruction aimed directly at the moving traveler. The staggering energy firmly required to reach the extreme speeds where this kinetic destruction truly begins vastly exceeds the total output of entire terrestrial civilizations. These two opposing paths are not independent engineering options. They are firmly the two extreme ends of a single, continuous physical spectrum, heavily governed by the exact same physical laws. The cosmos did not independently build two completely separate walls. It intelligently built one perfectly continuous barrier with two distinct faces. If humanity approaches slowly, time patiently devours the travelers. If humanity approaches quickly, physics violently devours the travelers. The immense space, strictly between these two extreme corridors, is precisely the space where any physical interstellar travel must mathematically occur. And every single point along that unyielding spectrum carries its own lethal, insurmountable combination of those exact same physical forces. This completely systemic nature of the barrier deeply explains why singular technological breakthroughs consistently fail to open the cosmos. Theoretical fusion propulsion heavily addresses the fundamental problem of thrust, but completely fails to solve the speed and fuel mass ratio requirements. Theoretical antimatter heavily addresses the requirement of raw speed, but completely fails to address the impossible industrial production requirements. Massive laser sails heavily address the specific problem of the onboard energy source, but completely fail to safely carry the heavy mass of a biological crew. Generation ships heavily address the problem of biological crew longevity, but completely fail to conquer the devastating degradation of deep time. Each highly specific engineering concept breaks exactly one isolated section of the chain, only to instantly find that the remaining, interconnected sections still hold absolutely firm, shifting the heavy, crushing load to a different point of inevitable failure. Furthermore, this chain strictly enforces profound, permanent isolation. The absolute physical limit of the speed of light guarantees a severe communication delay that permanently eliminates the concept of terrestrial ground support. A crew navigating a deep crisis cannot consult mission control, because any frantic request for help sent across the void will strictly require years just to reach Earth, and any possible response will require years more to return, arriving long after the crew has either solved the problem alone or died trying. This immense distance completely severs the fundamental relationship between the moving machine and the civilization that built it. It strictly dictates that absolutely no physical resupply and absolutely no physical rescue are even conceptually possible. The isolated ship must essentially contain an entirely self-sufficient miniature civilization. It must heavily carry not just spare parts, but the massive industrial factory tools to manufacture those spare parts. It must carry completely independent hospitals, complex agricultural farms, deep chemical synthesis facilities, and the continuous educational systems required to maintain highly specialized knowledge across centuries. Absolutely no human institution in the entire history of the Earth has ever achieved this terrifying level of total, permanent self-sufficiency without heavily relying on external trade, outside resources, or a surrounding, forgiving environment. An interstellar spacecraft possesses absolutely no surrounding environment. It is entirely confined within its own fragile hull, forced to carry everything a society requires to exist, or tragically resign itself to carrying nothing but ghosts into the dark. It is incredibly vital to precisely understand what this absolute barrier signifies. This conclusion is absolutely not a form of technological pessimism, nor is it a bold declaration that terrestrial science will simply cease to advance. It is a deep, profound recognition that the vast spaces firmly between the ancient stars are absolutely not mere gaps waiting for brilliant engineers to build clever bridges. They are the fundamental structural features of a highly specific universe firmly built upon exact physical constants, unyielding relationships between physical mass and raw energy, absolute structural limits on the precise speed of information, deep biological vulnerabilities embedded within terrestrial organisms, and the absolute terrifying rates at which entropy systematically degrades all highly ordered systems. Why fundamentally does not forbid physical objects from quietly entering interstellar space? Voyager 1 and Voyager 2 are deeply in interstellar space right at this exact moment, silently transmitting faint data back to Earth across a vast void that was once purely theoretical. Tiny, highly expendable robotic probes may eventually follow them within decades, accelerated by powerful lasers, safely carrying delicate instruments that can photograph another star system and faithfully send the slow images home to a waiting Earth. These robotic missions are physically possible, representing genuine engineering achievements completely within the reach of a near-future civilization. What the interlocking barriers absolutely prevent is not physical exploration. It is biological habitation. It is the physical, living transfer of fragile human beings directly from one specific stellar system to another, arriving completely alive, biologically functional, and fully capable of executing a meaningful purpose upon arrival. That specific, deeply romantic goal violently runs directly into the full, unyielding weight of the entire chain. The physical universe was simply not built for biological crossings at this staggering scale. It was fundamentally built for immense stars to violently burn in total isolation, permanently separated by vast, freezing distances that completely dwarf absolutely anything terrestrial biology has ever needed to physically traverse. Understanding this immense physical architecture with complete honesty absolutely does not fundamentally diminish the beauty of the dream. The profound desire to physically reach another star remains among the most exceptionally beautiful, deeply human impulses the conscious mind has ever produced. It emerges directly from the exact same capacity for boundless wonder that boldly drove the ancient Polynesians across the vast, terrifying Pacific Ocean and forcefully pushed the Apollo astronauts to step foot onto the desolate surface of the moon. But deep wonder and physical capability are completely different forces of nature. The Pacific Ocean was crossable precisely because wind, physical water, and raw human endurance reliably operated on specific scales that mathematically matched the physical distance. The moon was successfully reachable precisely because conventional chemical rockets and a 3-day transit time comfortably operated on scales that matched the specific challenge. The distant stars absolutely do not mathematically match. The scales are violently, completely wrong. The distances are incomprehensibly large. The energy is impossibly extreme. The required timescales are hopelessly long, and the interstellar medium is far too hostile for the fragile biological and delicate mechanical systems that all human beings completely depend upon for survival. And perhaps, upon deep reflection, that is absolutely not a tragedy. Perhaps it is simply what the physical universe inherently is. A place of staggering, violent beauty that must be safely observed from positions of profound, permanent confinement. Humanity can beautifully see the distant stars, meticulously study their ancient light, precisely identify their hidden planets, carefully analyze their atmospheres, and deeply calculate whether alien life might theoretically exist on their far-off surfaces. Humanity can bravely send tiny, silent machines deep into the freezing interstellar medium and patiently listen for their whispered radio signals crossing light days and eventually light years of absolute distance. Humanity can intimately know the vast cosmos with extraordinary precision directly from exactly where it is currently standing. What humanity almost certainly cannot ever do, strictly within any timescale that maps onto human civilization as we currently comprehend it, is physically walk there. Right now, in the freezing dark, Voyager 1 is still out there. As these quiet words are spoken, it is drifting completely alone through the dense interstellar plasma at 17 kilometers per second. Its faint radio signal, severely weakened to a ghost of a whisper after traveling for nearly a full light day, still miraculously reaches the massive deep space network antennas positioned on Earth. Engineers meticulously send commands and patiently receive responses, though each slow exchange now takes nearly 48 hours to complete a round trip. Most of its delicate scientific instruments are entirely silent. Its failing power source, a small lump of steadily decaying plutonium, currently generates less electricity than 3 household light bulbs. Within a very few short years, even that tiny output will fall far below the critical threshold strictly needed to run anything at all. Voyager 1 will eventually go entirely quiet. It will steadily continue traveling. It will absolutely not stop. Nothing located in deep interstellar space will physically slow it down appreciably for billions of silent years. In approximately 40,000 years, the silent machine will silently pass within about 1.6 light-years of a distant star called Gliese 445 in the constellation Camelopardalis. It will not physically stop there. It will absolutely not enter a stable orbit. It will drift past entirely unnoticed, silently carrying a fragile golden record deeply encoded with spoken greetings in 55 human languages, complex music ranging from Bach to Chuck Berry, the faint sound of a human heartbeat, and the recorded brainwaves of a woman deeply thinking about love and the vast history of Earth. No one in the dark will play it. The physical distance is simply too vast, and the silence is completely too deep. The silent golden record will completely outlast the civilization that proudly made it by a terrifying interval that completely dwarfs the entire recorded span of human history. But the physical record exists, and so does the profound human dream, and so does the meticulous knowledge, hard-won and brutally precise, of exactly why the distant stars strictly remain completely beyond our physical reach. The universe absolutely did not build one single wall between humanity and the stars. It intelligently built a chain. Distance, time, energy, speed, radiation, dust, biology, mechanics, isolation, and communication. Each unyielding link is forged strictly from fundamental physics. Each rigid link is flawlessly welded to the next. No single scientific breakthrough severs the chain because absolutely no single link bears the heavy load entirely alone. The crushing weight is perfectly distributed. The immense structure strictly holds. This is absolutely not a locked physical gate with a magical key cleverly hidden in the distant future. It is the profound, absolute shape of the physical universe itself, flawlessly expressed in the vast distances firmly between the ancient stars and the strict mathematical constants that heavily govern mass, energy, and light. The massive stars violently burn in the dark. The silent void stretches perfectly between them. And we, firmly confined on our small, fragile world, look deeply upward with a profound longing that physics fundamentally cannot answer, but with a deep clarity that perhaps only cold physics can truly provide. The absolute barrier the universe built is absolutely not cruelty. It is perfect, unyielding architecture. And understanding that architecture honestly, deeply, and completely may ironically be the closest we ever truly come to successfully crossing the vast, silent dark. We have traveled to the absolute edges of human possibility tonight, mapping the precise boundaries of our cosmic confinement. We have seen how the universe did not simply build a single wall, but carefully forged an unbreakable chain of distance, time, energy, and radiation, heavily guarding the vast spaces between the stars. The architecture of reality mathematically demands that we remain exactly where we were born. Yet, within this profound, permanent isolation, there is an undeniable, breathtaking beauty. Our fragile physical bodies are strictly bound to this single blue world, but our conscious minds are allowed to roam freely across the infinite dark, measuring the exact distance to Proxima Centauri, understanding the heavy fabric of spacetime, and decoding the ancient light of alien suns. The distant stars will continue to violently burn, completely unreachable, and humanity will patiently continue to watch them, completely unyielding in our endless curiosity. The universe is vastly larger and far older than we can easily comprehend, but for a brief moment tonight, we held its true scale in our thoughts. This brings our journey into the silent void to a gentle close. If you found a strange sense of peace in the cold mathematics of the cosmos, and if you deeply appreciate exploring the profound mysteries that surround our tiny world, please consider leaving a like and subscribing to Bedtime Universe. Your quiet support helps this channel continue to pull back the heavy curtain on the grand architecture of reality. Share your deep thoughts down in the comments below. Let us know which unyielding physical barrier you believe is the most terrifying, or perhaps the most beautiful. Until the next time we journey into the dark together, close your eyes, rest well, and always remember that even in our complete isolation, we remain a conscious, observing part of this magnificent universe. Good night.